Hello everyone. On this video we will be going over limits and continuity of several variable functions. Okay, so to get started, first thing we're going to do is take a little review. That's for the real valued function definition of a limit. Okay, so for that definition, it says for any epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of f of x minus your limit is less than epsilon whenever 0 is less than x minus a is less than delta, which means the limit of f of x as x approaches a equals that limit. Okay, so really all this means is that the distance between your function and your limit gets smaller when the distance between x and a gets smaller. So epsilon and delta just represents a really small number. Okay, never 0, it'll never equal 0, it's just a really small number. Alright, so to kind of help visualize it, move that up a little bit. Okay, so we have our x and we have our y-axis. Let's say this is our function. Okay, so let's say this is our f of x here. Okay, so let's say that we have our a value. This is our limit when x is equal to a. Okay, so we're saying that as you get closer, so let's say this is L plus our epsilon, and this is our limit minus some value epsilon. And this value here is our a minus some small value delta. And this is a plus some value delta. Okay, so what they're saying is the distance for some x equals a, if this is your x value here, and if you're getting closer and closer and closer and closer to a, as that x value here gets closer to a, this gets closer to the limit. Same if you're approaching that value from the left. If it's getting closer and closer to a at the same time, this is just getting closer and closer to your limit value. Okay, so this is the single variable explanation of a limit. Let's look at the three-dimensional explanation for a variable of a limit. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and go to the next page. Yep. Straighten up my papers there. There we go. Okay, now we're going to look at three dimensions. Definition of the limit of a function with two variables. All right. So what if we let f be a function of two variables. Defined. Okay, now it's possibly it won't be defined at the point, except possibly at the point x0, y0. Okay, and that's on an open disk centered at that x0, y0. Okay, and we're going to let L be a real number. Okay, so that means for any epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of your two variable function minus your limit is less than epsilon whenever 0 is less than the distance of x minus x0 squared plus y minus y0 squared, which is less than delta. Remember, that's just your distance formula. All right, so to kind of explain what all this means, I'll draw a little 3D graph here. So let's draw our three-dimensional plane where we have our x, we have our y, and we have our z. Okay, so again, we have some value here. This will be your x0. Let's say this is your y0 here. Okay, so your x0 goes out here, and your y0 goes out here, which makes that point your x0, y0. Okay, so what we're going to look at, we're going to look at just the space around that x0, y0. Okay, so what we're going to do is that space there, we're just going to enlarge it to where that's the space there. And right in the middle is your x0, y0. Okay, so that means from any direction, because remember, when you're in 3D space, it can come from any direction at all. When you're just looking at the xy axis, you can approach a value from the left or you can approach it from the right. With this one, you can approach from the left, or the right, from the top, the bottom, at an angle. You can approach it an infinite number of directions. Okay, so what we're looking at is when they get within that delta, this is what you call the delta neighborhood. About your x0, y0. Okay. Now, when you have less than or greater than, that's why we have the dotted disk. That's when you know it's an open disk. It's kind of like if you graph a line. If it's less than, then you use the dotted line. If it's less than or equal to, you use the solid line. Same thing. Okay, so if you have less than or equal to or greater than or equal to, it's a closed disk, which just means that's a solid circle. Okay, so that's kind of a quick explanation before we kind of jump into the, hopefully this will help you visualize what you're doing. All right, so if you're still writing, feel free to press pause, but we're going to jump right into our first example. All right, so let's say, for example, we wanted to evaluate the limit of 5x squared y over x squared plus y squared as x and y approaches 0 and 0. Okay, now normally, first thing you want to do is just plug those in. Okay, but if we plug in x equals 0 and y equals 0, we just end up with 0 over 0. Okay, so that gives 0 over 0. Okay, remember now we have two variables. We can't use L'Hopital's rule. Okay, so there's no L'Hopital's rule here because we can't use it because we have two different variables. Okay, so now what we're going to do is we're going to see exactly what will happen if we approach this function from different directions to find our limit. Okay, so what if we approach it along the y-axis? Okay. And really the y-axis just means that x is equal to 0. Okay, so if we're approaching that along the y-axis and our x is equal to 0, that just means we make all of our x's 0. So the limit of 5 times 0 squared y over 0 squared plus y squared as xy approaches 0, 0, or you could just say 0y, is equal to 0 over y squared, which is equal to 0. Okay. Now, what if we decide to approach it along the x-axis? Okay. Remember, on the x-axis, that's just your y is equal to 0. Okay. So that just means that your limit 5x squared, turn y into 0, over x squared plus 0 squared as xy approaches 0, 0. That's going to equal 0 over x squared, which is still 0. Okay, now we approached it from two different angles. We could do more, but just for right now, we're going to say that it's safe to estimate that this limit is 0. I'm going to show you a few other methods a little later, but we're going to estimate that this has a limit of 0. Somewhat. To estimate the limit is 0. Okay, but the definition will verify it. All right, so we're going to use the definition. Go ahead and write that out instead of trying to have you remember it. For any epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of f of x, y, minus the limit is less than epsilon whenever 0 is less than square root x minus x0 squared plus y minus y0 squared is less than delta. Okay, so we have our definition. Okay, now we want to prove that the limit of 0 is true. We have our x0 and y0. That's our x0 and y0. Okay, so if we plug this in, our f of xy is just 5x squared y over x squared plus y squared. Okay, so our f of xy, 5x squared y over x squared plus y squared, minus the limit, I'll just put minus 0, even though you don't have to, less than epsilon whenever 0 is less than the square root of x minus x0, so that's x minus 0 squared plus y minus 0 squared. Okay, remember these two, as x and y approaches, that's your x0, that's your y0. That's less than delta. Okay, so kind of simplifying these and taking away those zeros, it's going to be the absolute value of 5x squared y over x squared plus y squared less than epsilon whenever 0 is less than the square root. X minus 0 is just x, so x squared plus y squared is less than delta. Okay, so this step requires looking for little details. Okay, now what's the one thing you can notice? You can really go in various directions with this, but just if we notice, okay, that x squared over x squared plus y squared is less than or equal to 1. Okay, like I said, just one of the things we noticed. All right, so what can we do with that? Well, if we factor out the 5 and the y, you can work with that. Okay, so if we factor out, so let's say 5x squared y over x squared plus y squared, that's going to equal, factoring out the 5y, so 5 absolute value of y, because it's absolute value of everything in there, times the absolute value of x squared over x squared plus y squared. Okay, now what did we figure out? That x squared over x squared plus y squared is less than 1. So that means 5 times absolute value of y times x squared over x squared plus y squared would be less than or equal to 5 times absolute value of y times 1. Because if we just multiply both sides by 5 times absolute value of y, we'll end up with this. Okay. Now what else are we going to notice? Okay. Well, right now we can notice that absolute value of y, I'll put that in a little box, is actually less than or equal to, let's say if you have the square root of y squared, that's just y. So the square root of y squared, y, absolute value of y, will be equal to that. Okay, but what if we have x squared plus y squared? Then that absolute value of y is going to be either less than or equal to, depending on if x is equal to 0. If x is not equal to 0, then this is going to be true. Or x and y is not equal to 0. But if just x is equal to 0, this is true. If x is not equal to 0, this is true. So this is true all around. Okay, so that means that if we multiply both of these sides by 5, you have 5 times absolute value of y is less than or equal to 5 times the square root of x squared plus y squared. Okay, and what was given to us? Square root of x squared plus y squared is less than delta. So that's less than 5 delta. Okay, now what do we do from there? Well, what if we get rid of that 5 by letting delta equal e over 5, or epsilon over 5? Okay, so if we let delta equal epsilon over 5, then that's going to equal 5 times epsilon over 5. When those two cancel out, that's just going to equal epsilon. Okay, so this long trail just showed us that the absolute value of our function minus the limit is less than epsilon whenever this is true. Okay, so this just proves that 0 is the limit. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and do our next example. Uh-oh. Paper's getting sticky there. There we go. Didn't want to slide down. All right, so let's say for this example, what if we wanted to evaluate the limit of x plus 3y squared as xy approaches to 1? Okay. Now in this case, you can use direct substitution because you won't create an interdeterminate or you won't create an undefined value. Okay, so if you just make x equals 2, y equals 1 using direct substitution. Okay, now I advise trying direct substitution first. Okay, so a lot of times if you do direct substitution, 10 seconds later you have your answer. Okay, so that will give us the limit of 2 plus 3 times 1 squared as xy approaches to 1. And really, that just ends up being 2 plus 3 times 1, which is 3, which is 5. Okay, now the fact that you plugged in your x0 and y0 and it gave you the limit value shows that this function is continuous at 2, 1. Okay, which covers the next definition, continuity of a function. of two variables. Function with two variables. Okay, so what that says is a function f of two variables is continuous at a point x0, y0 in an open region of R, so pretty much anywhere around it, that open region, if f of x0, y0 is equal to the limit of f of xy as xy approaches your x0, y0. Okay. Now in a formula term, that's just meaning that the limit of f of xy as your x and y approaches your x0, y0 is equal to f of x0, y0. Okay, so if we use this definition here, all this means is that 5, our limit, is equal to f of 2, 1. We replace x with 2 and y with 1, we got 5. So that's your x0 and y0. Okay, so if, in other words, if direct substitution leads to a limit value, the function is continuous at that spot. At that point. All right, so this is the drawn out explanation of it. This is kind of the get to the point explanation of it. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and go to our next example. There we go. All right, so let's say for this example, what if we wanted to evaluate the limit of the natural log of x squared plus y squared as xy approaches 0, 0. All right, so this one, again, just using direct substitution, limit of the natural log of x squared plus y squared as xy approaches 0, 0. We plug in x equals 0 and y equals 0. That's just the natural log of 0, which is negative infinity. Okay, so of course, if your limit is negative infinity or positive infinity, then it doesn't exist. Okay, so the limit does not exist, but is continuous everywhere except at the point 0, 0. Okay, you can plug in 0 and 0.1 and you'll get a value. That's the only point that it does not exist. All right, so you kind of look, just to kind of give you an idea of what that means. You look at a two-dimensional drawing of natural log of x. So you have your x, you have your y. Natural log of x looks like this. In 2 dimensions. Okay, now in 3 dimensions, you have your natural log of x squared plus y squared. That kind of looks like a funnel. So if you have kind of looks something like that. Of course, if you just Google the natural log of x squared plus y squared 3D graph, it'll give you a much better picture. But that's just if you're curious as to what it would actually look like. All right. Okay, so if you are still writing, feel free to press pause. But we're going to go ahead and go to our next example. All right, so let's say for this example, we want to use polar coordinates. To find the limit of, okay, let's say we have the limit of x squared plus y squared times the natural log of x squared plus y squared as xy approaches 0, 0. All right. Now with this one, first thing you want to do is notice they said polar coordinates. So when they say the polar coordinates, you know that x is equal to r cosine theta, y is equal to r sine of theta, and I'll put the other one first. X squared plus y squared is equal to r squared. Okay, all of the equations from your polar coordinates. All right, so we just replace these. So if we replace your x squared plus y squared with r squared, that gives you the limit of r squared times the natural log of r squared. Instead of xy approaching 0, we're going to have your r approach 0. Okay. Now, if you remember from, I believe it's a couple of trig classes, maybe, can't remember exactly which class, but natural log should be in intermediate algebra. natural log of r squared is equal to, you can bring that 2 down to the front for the power rule of log. So it's 2 times natural log of r. And our r squared, you can actually rewrite that as 1. Get a new pencil lead here. There we go. You can rewrite that as 1 over r squared. All right. So that means we're going to rewrite this as the limit of 2 natural log of r over 1 over r squared as r approaches 0. Okay. Now, if you remember the last couple of examples, we couldn't use L'Hopital's rule because we had 2 variables. Okay, but now we have 1 variable, so we can use L'Hopital's rule. Okay, so use L'Hopital's rule since we have only 1 variable. Okay, so we have the limit as r approaches 0. The derivative of natural log of r is 1 over r. So you have 2 times 1 over r, which is 2 over r. And the derivative of 1 over r squared is negative 2 over r to the third. Okay, so actually, if you divide these two, let me write this out. I'll write this down at the bottom, kind of out of the way. Two over r divided by negative 2 over r to the third. You rewrite that, you have 2 over r times negative r to the third over 2. So those cancels out, and that really leaves you with negative r squared. So what we have here, I can actually move that back up. We're almost done. You have the limit r approaches 0 of negative r squared, which is really just 0. Okay, so whenever you see an example for polar coordinates, you have to start off with your polar coordinates for x, y, and z, and that would help. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to the next example. All right, separate their papers. There we go. All right. Now, quick note here. If you have a limit that fails to exist, so if the limit of f of x, y fails to exist, as your xy approaches your x0, y0 along some smooth curve, or let's say if it has different limits, f of x, y has different limits. as your xy approaches your x0, y0. Along two different curves. So along two different smooth curves. Then the limit of your f of x, y does not exist as your xy approaches x0, y0. All right, so really all this means that if you calculate the limit and it goes to negative infinity or positive infinity, the limit doesn't exist. If you approach the same point and you get two different values, that limit does not exist. So that's really all this is saying. And I'll give you a quick example. We already saw one where it approached negative infinity. But let's say if we wanted to evaluate, so if we evaluate the limit of negative xy over x squared plus y squared as xy approaches 0, 0. All right, so what if we do just like we did before from our first example? We use the first example, and we go along the y-axis. Or in other words, x equals 0. Okay, so that means you have the limit of negative 0 times y over 0 squared plus y squared as xy approaches 0, 0. And you get 0 over y squared, which is 0. And honestly, if we did the same thing with y equals 0, we get 0 again. But what, instead of going, let's draw a little xy axis here. So if your x, your y, and your z, okay, instead of going along the y-axis, or then again the x-axis, what if we come out at an angle, approach it at a slant? Okay, so if we approach that point at a slant, we can see if it has the same limit. Okay, so what if we go along y equals x? Okay, so now we're not approaching it coming down the x-axis or the y-axis. We're coming at an angle. Remember, y equals x is a diagonal on the xy axis. Okay, so that would mean you have the limit y equals x, so that's negative x times x over x squared plus x squared as xy approaches 0, 0. Okay, so if we have that, you have x times x, which is x squared. So you have negative x squared over x squared plus x squared is 2x squared. These two cancels out, which leaves you with negative 1/2. Okay, so here you have a limit. If you approach it from the x-axis, you have a limit of 0. But if you approach it from a diagonal, you have a limit of negative 1/2. So since you have two different limits approaching the same point, the limit doesn't exist. So the limit does not exist. Remember, I usually say D and E as xy approaches 0, 0. All right. Okay. Now this was really, really close to the first example we did. So what makes this one different than the first one? Okay. So we'll take a quick look at that one. We'll re-look at it. Okay. So if you're still writing, feel free to press pause. But we're going to go ahead and kind of look back at that question. Okay, so if you remember, I believe it was example 1, where we had to evaluate the limit of 5x squared y over x squared plus y squared as xy approaches 0, 0. Let me clean that up a little bit. Here we go. And make limit a little bit bigger. Okay, so our very first example. Okay, so if we went along, we saw that approaching along the x and y axis gave a limit of 0. Okay, so we kind of just stopped after those two. But what if we wanted to try going along the x-axis? I mean, along y equals x. Okay, so we're going to approach this at an angle of y equals x. Okay, so it means you have the limit of 5x squared, y equals x, so you're going to replace that with x, over x squared plus y equals x, so you're going to have x squared again as xy approaches 0, 0. Okay, so that means you have 5x to the third over x squared plus x squared is 2x squared as xy approaches 0, 0. Okay, so when these cancel out, you're going to get 5x over 2. I'll put that underneath since I'm running out of room. Well, I might be able to fit it there. So you have the limit of 5x over 2. Remember, that's as xy approaches 0, 0. So if you plug in 0, you get 0 over 2, which is 0. So that's equal to 0. Okay, so we have the same limit that we had before. But what if you try a different direction? What if we try approaching it along y equals x squared? Okay, so now we're going to try approaching it from a parabola angle. Okay, so if we do that, we have the limit. And again, we're going to replace y with x squared of 5x squared times x squared over x squared plus x squared squared. So x squared plus x squared squared as xy approaches 0, 0. Okay, so what does that give us? That gives us the limit as xy approaches 0, 0 of 5x to the fourth over x squared plus x to the fourth. Okay, so that gives us the limit as xy approaches 0, 0, 5x to the fourth over, we factor x squared out of both of those. We have x squared, 1 plus x squared. This cancels out with 2 of those, so we have x squared. So that leaves us with, I'll put that underneath since we're out of room, the limit of 5x squared over 1 plus x squared as xy approaches 0, 0. Again, that's 0 over 1, which would still be 0. Okay, so let's try one more along, let's say y equals some linear function of x. Okay, so y equals mx. Okay, so the limit, we have the limit as xy approaches 0, 0. And we're going to replace every y with mx. So we have 5x squared times mx over x squared plus mx squared, okay, which equals the limit, again, as xy approaches 0, 0. We simplify that. We have 5x to the third times m over x squared plus m squared x squared. Okay, so we're going to factor x squared out of the denominator. So we have the limit xy approaches 0, 0 of, let's say, 5x to the third times m over x squared. We have 1 plus m squared. Okay, so this x squared cancels, and this cancels out and leaves just x to the first power. There we go. So that's going to equal the limit as xy approaches 0, 0 of 5mx over 1 plus m squared. And x comes 0, which gives us a limit of 0. So no matter how we approach this, or what angle or what direction we approach this, even though there are an infinite number of possible ways we can approach it, we should have a limit of 0 if the limit, the same limit. This could have been a limit of 2, 2, 2. It doesn't matter. As long as you have the same limit, no matter what direction you approach your function from, your limit exists. Okay. Now, the minute we plug one in, it doesn't matter if this says 0, 0. If this comes up and it's -4, then that limit doesn't exist. It just takes one time to get a different limit value for it not to exist. But because the limit that we did first, remember the first time we did it, we got a limit of 0. Then we approached it at different angles. Every time we still got a limit of 0. So that's how we know, you know what? We're right, the limit is 0. Alright, so hopefully this made sense, and I will see you on the next video.